Congratulations. You've made it to Chapter 4 in our study of elementary calculus, and in this chapter we're going to be learning about calculating the derivative. And in our first section, let's look at some techniques for finding derivatives. You have already learned one technique for finding the derivative, and that technique involved using the limit. And the great news that I have for you is that we're going to use a much faster process now for calculating the derivative. As a reminder, notations for the derivative, this is one of the most frequently used. We say f prime. That represents the first derivative of the function f. dy over dx, which is really lowercase delta y over lowercase delta x, which is change in y over change in x, which is slope, which is rate of change. And I'm talking about instantaneous rate of change here. And then these are a couple of other notations that you see occasionally. This one you'll almost never see. This one, yeah, with some frequency you'll see it. You should know that this is read the derivative of y with respect to x. If you're in an elementary calculus course, chances are you're not going any further in your study of calculus, but it is possible that you could have an equation with multiple variables in it and only be taking the derivative with respect to one of those variables. Hopefully we'll have the chance to talk about implicit differentiation in this course, in which case what you're taking the derivative with respect to will become a little bit more important. And now for the specific techniques of finding the derivative without using a limit. Here we're being told that our function f of x is equal to just a number, a real number k. And what we're doing here in finding the first derivative is finding the derivative of k with respect to x. And the fact that it's equal to 0 means that the derivative of any constant value is going to equal 0. Well, that sounds nice. If it's the derivative of a constant, it's 0. I'm not going to answer the question why very frequently, but in this case, let's say that your original function was f of x equals 2. Let's draw a graph of that function. There it is, f of x equals 2. What would you say is the slope of this line right here? I'd say it's 0. And what about the slope of the line here? What about the rate of change there? 0 again. If you pick any point on this horizontal line that has the equation y equals, or f of x equals 2, you'll find that the rate of change of y with respect to x, rise over run, the slope at any given point is equal to 0. And that's why the first derivative of a constant function is equal to 0 everywhere. So if this is f of x equals 2, f prime of, I don't care what number you put in here, will be equal to 0. Because when x is equal to 1, or negative 3.5, or pi, or e, or whatever, the slope of the tangent line, the rate of the change at that x value will still be equal to 0. Okay, so the first derivative of a constant is equal to 0. What if I'm now working with a variable, and that variable is being raised to the nth power? Then the first derivative of our function, or the derivative of x to the n with respect to x, is equal to, and here's where it gets nice, and this is where you really want to be committing this pattern to memory. You're going to be doing, we're going to talk a lot about it in this section. You're going to do it over and over and over again as part of your homework assignments. This is what we've been building to so far in this course in terms of the really process-oriented task of finding a derivative. if you're given x to the n, and you take this n and you multiply it by the coefficient that's already there, which is 1, then you will get a new coefficient of n, and the variable is still there, and then we're going to take this exponent of n and we're going to decrease it by 1. So it will turn into n minus 1. And this is what you're seeing here. So the first derivative of x to the power of n is equal to n times x to the n minus 1. We took the exponent, we multiplied it out front of the variable, and then we decreased the exponent by 1. You're going to get good at this process. You will get very efficient at this. Be mindful while you're doing this that at some point in the relatively near future, we're going to have to do it backwards. Everything that we're doing in this chapter, at some point in time, we will need to undo. Just like foiling was the first thing we learned how to do, and then we had to learn how to do it backwards and learn how to factor. Very similar. This is a derivative. We will learn about antiderivatives. All right, so that's nice. And a thing that's unique about what we're talking about here is that this variable initially has a leading coefficient of 1. And you can see it in here also. Right in there is an invisible number 1 in front of that x. So this table is showing us some examples. If we have x to the first power, we take that exponent of 1, we multiply it in front of our variable, and then we decrease this exponent by 1, which makes it a 0, which means we have 1 times x to the 0. Anything to the power of 0 is equal to 1, so we really have 1 times 1, which is 1. So the first derivative of x is equal to 1. Again, I'm not going to do this very frequently, but in this particular instance, it's quite easy. Let's graph f of x equals x. In other words, y equals x. There it is. The graph of y equals x. And what's the rate of change of our function right here? What's the slope of our function right here? What's the slope of the tangent line here? It's 1 at every point on the graph. So that's why it's such a sort of basic looking result where we're saying in here that f prime of x is equal to 1. So that's the first derivative of the function x is equal to just 1. Now let's look at the next one. X to the second power. Take the exponent, multiply it out front. So 2 times 1 is now equal to 2. And then decrease the exponent by 1 and it becomes a 1. So you have 2 as the new coefficient, 1 as the new exponent, which means 2x is the derivative of x squared. Don't memorize any of this table. I'm just using the table to get you into the rhythm of taking the derivative of something that's of this format, x to the n. And the rhythm is exponent multiplies out front, decrease the exponent by 1. Or if you want to rephrase that, rephrase it. But figure out the language for it and then burn it into your brain. Not literally. What if the variable doesn't have a leading coefficient of 1? For example, here we see that our function is equal to k times some expression. For example, well, let's just roll with what's printed here. So here we're taking the first derivative, in other words, the derivative with respect to x of k times g of x. And what the next thing says in this little equation is that we can take this variable of k out of the process. We can factor out that multiple of k and write it as k times g prime. I don't love that they wrote it this way at this point. I wouldn't have written it that way just there. I would have instead written k times d over dx of g of x. That way, we're going from, let me get rid of some of this other scribble. I like the idea of going from, well, let's try it with yellow. From here to here. The only thing that's changed in those two statements is that the k has gone from the inside of the derivative process to the outside on the left. Let's move to the outside of the derivative process. Still attached to the process by multiplication. We're going to see an example of this, I promise, but I want you to see it in generality. This you already know from our limit laws. We said that the limit of a sum is equal to the sum of the limits. Here, we see that the, and again, they're mixing their notation here, which I still don't love. The derivative, the derivative of a sum is equal to the sum of the derivatives. So it's almost like the distributive property of taking a derivative, where you're distributing over addition or subtraction. So let me illustrate those things for you in this example. F prime of x, so the derivative, is equal to, I'm even going to write it using d over dx of this entire statement, 2x squared plus 9x plus 4. Okay, so first I'm going to distribute this derivative over addition. So I'm going to distribute the derivative to here, and I'll distribute it to here, and I'll distribute it to here, to all three of my terms. Let's see. This equals then d over dx of 2x squared plus d over dx of 9x plus the first derivative of our constant value 4. So there we sort of distributed, and you can match that up to the properties that we just chatted about in the previous pages, previous slides. Now, I'm going to factor out a couple of constant values. I'm going to take this 2 right here, and I'm going to factor it out in front of the derivative process. I'm going to do the same thing with this 9. I'm going to factor it out front here, so that we get 2 times the derivative with respect to x of x squared plus 9 times the first derivative of x plus the derivative of our constant value 4. So we've sort of dismantled this derivative statement as much as possible. Now let's actually take the derivative. So this is equal to 2 times, now what's the derivative of x squared? We take the exponent of 2 and we multiply it sort of out front of the variable. So there's the 2 times x, and then we decrease the exponent by 1. So I'll write 2 minus 1 plus, here's the 9 times, and then the exponent of 1 in here is invisible, but if you'd like to write it, you can. It's not very typical that we would write it, times x to the 1 minus 1 plus, and then as you might recall, the derivative of a constant value is 0. And then we'll go through and clean things up a little bit, or a lot. So the 2 times 2 makes 4. The new exponent on x is a 1, so I'm not going to write that, plus 9 times 1 times anything to the power of 0 is also equal to 1. So this really equals 9 times 1, which is just 9. So 4x plus 9 is your answer. Yeah, okay, it's shorter than the previous derivative process that we worked with. I don't know that I'm in love with it, but okay, I'll buy it. It's shorter. I have to learn some new things in order to do it this shorter way. I guess I like learning new things. I was kind of, right, Newback, you were kind of excited about this. I thought it was going to be really fast. Check this out. What's 2 times 2? 4. What's 2 minus 1? 1. X to the first power, nobody writes that. Plus, what's 1 times 9? How about 9? And what's an exponent of 1 minus 1? Well, 1 minus 1 is 0. What's x to the 0? 1. So this is really 9 times 1. But nobody writes 9 times 1, you just write the 9. Hey, look at that. 4x plus 9. Guess what the first derivative is? 4x plus 9. So if you know how to multiply and subtract, you could pretty much take that derivative in your head. Let's see if we can use this little, even shorter technique that I used up here in red. Let's try to implement that as we take the first derivative of this expression, or this function. I'm going to take the exponent of 7/5 and I'm going to multiply it times the leading coefficient. And then we're going to keep the variable and we're going to decrease the exponent by 1. 7/5 minus 1. Let's go to the next term, minus the existing coefficient. We're going to multiply the exponent times that existing coefficient, so let's multiply it by 2, and then we'll keep the variable and we'll decrease the exponent by 1. Plus, this is a constant value. The derivative of a constant is 0. So we'll put plus 0. And then let's go through and clean it up. This is 63/5, which is unfortunate, but it is what it is, times x to the 7/5 minus 5/5 equals 2/5. So that's our first term. And then in the second term, subtraction, 5 times 2 is 10. Keep the variable. Our new exponent is a 1, so I'm not going to write it. Plus 0, not going to write it. And that's your first derivative. Now that's fast. I like that. I wish it would have been so fast for the past couple of weeks, right? Instead of all those limits and sending h to 0 and using the difference quotient. What a nightmare. Oh, what about this? What's going on here? How am I supposed to subtract things from exponents here? It's typical that math problems, as we're learning within any given topic, it's typical that the problems become more difficult by adding additional steps to the beginning of the process. And here we have a couple of additional things we're going to need to do in order to prepare this function so that we can work with it just like we did the previous functions. We need some exponents. And I don't love that my variables are in the denominator. So let's see what we can do. All right, f prime. I need a different color. I'm going to mix it up every once in a while. f prime of x is equal to, oh no, I'm not going to do that. Let's just write f of x. Let's rewrite our function. And I'm going to write this as 4 times x to the negative 1/2. Now remember that a variable to the 1/2 power is the same thing as a square root. Let's put a little note somewhere if you want. If you're comfortable with this, you don't have to write this down. That let's say that if you're taking the nth root of x, that's equivalent to x to the 1 over n power. So you know this from college algebra, converting back and forth between radical notation and exponential notation. Another thing that you learned as part of that topic was that where should I put this? Let's go with 1 over x to the m is equivalent to x to the negative m. So that allows me to bring my variable up into the numerator. And the other thing that you learned sort of takes this topic to the moon, or at least to the next level, is that if you have the nth root of x to the m, that can be written in exponential form as x to the m over n. So the denominator of those exponents is, I call it the degree of the root. This n value right here, technically it's called the index. But I like calling it the degree of the root because on a tree the roots are on the bottom, and in this fraction the number on the bottom pertains to the root. Alright, so using those 3 topics, which you're supposed to know coming into this course, I'm holding you to it, allows me to change this division by x, the square root of x, to x to the negative 1/2 power, minus 4 times x to the negative 1, plus 4 times x to the negative 3. So the negative in the exponent position shoves it back down into the denominator, and those fractional exponents pertain to roots. Now I don't have any more denominators, at least my variable's not in the denominator. That's what I was really concerned with. So get the variable out of the denominator. I'm not going to write it out. You write it out. My handwriting looks pretty much like that anyway. Now let's take the derivative. Maybe now I'll switch colors because we're actually taking the derivative. F prime of x is equal to the existing coefficient times the exponent times the variable to the original power minus 1 minus 4 times the next exponent times the variable to the exponent minus 1 plus 4 times the exponent of negative 3 times the variable to the original exponent minus 1. So the exponent times the coefficient decrease the exponent by 1. Say it with me now. Take the exponent, multiply it by the coefficient, and then decrease the exponent by 1. That's what I just did 3 times in a row here. And after that, it's housekeeping. You just got to clean this up, make it look better. I've got negative 2, because half of 4 is 2. You see the multiple of the negative there. And I've got x to the negative 3/2 power. I've got a double negative in here, so that's going to become plus 4 times x to the negative 2nd power. Double negative, or sorry, a single negative there. A positive times a negative makes negative. 4 and 3 makes 12. And x to the negative 4th power. You could present this as your final answer. This does say negative 3/2, by the way. You could present this as your final answer, or we could convert it from exponential notation back into a radical notation, writing our answer without any negative exponents. So I'm going to write this as negative 2 over, watch me now, the square root of x to the third. The negative is here, the 2 is here, the x is here, and then that exponent, well, you just got to practice, brush up on that stuff. Next, plus, not with a highlighter, plus, let's write this as 4 over x squared. The negative in the exponent pushed us into the denominator, and then the 2 came with it, became positive instead of negative, minus 12 over x to the fourth. My guess is that this is what you're going to be typing in as a final answer, or that you would see as a multiple choice option potentially. All right, looks good. This is kind of mean. We're going to learn in the very near future a faster way to do this problem, but at the moment, in order for you to solve this, you're going to want to FOIL this, combine like terms, and then take the derivative using the same process that we just did. All right, so yeah, making sure that you're up on your exponents and converting back and forth between exponential notation and radical notation. Find the slope of the line tangent to the graph of this equation at x equals 4. All you have to do in this problem is find y prime, which is the same thing as f prime of x. And then the next thing you'll do, once you have your first derivative, is you'll take a 4 and you'll plug it into your derivative equation. All right. Yep, you can do that. Find the equation of the line that's tangent to this equation at x equals -2. In order to write the equation of a line, you need point slope form. That's how I would do this. Point slope form. That's point slope form of a line is y minus y1 equals slope m times x minus x1. In order to utilize point slope form, you need a point, x1, y1, and you need a slope, m. How am I supposed to find my point? Well, you've been given the x coordinate of a point on this graph. Take that x value, plug it into the equation, and come up with a y value. So your point, x1, y1, is going to be -2 comma something. How am I supposed to find my slope? Well, slope is f prime. You want a specific slope. You want the slope when x equals -2. So you'll need to take the first derivative of your equation, f prime of x, in other words, y prime, and once you've determined what f prime of x is, you'll take and plug in an x value of -2, and that will give you your slope. Alright, so I think that you can handle doing those two things. I will tell you that your first derivative, y prime, is equal to 2x minus 1, this otherwise known as f prime of x. Alright, I'm going to leave you to find the y value that goes along with your x coordinate, and then I'll also leave you to take your value of -2 and plug it in here in order to find your slope. 2x minus 1. Okay, and find all points on the graph of this function whose tangent lines are parallel to this other line. Well, I know that parallel lines have the same slope as each other, so I better figure out the slope of this line over here. Let's figure that out. I'm going to add 22x to both sides so that I get the equation y equals 22x. This is my slope, a slope of 22. So now I want to find all the points on the graph f of x equals 2x squared plus 6x where the tangent at that point has a slope of 22. That's irritating, but we can do it. First, we're going to need the first derivative of our function, f of x. So I take the exponent of 2, I multiply it by this 2, I get a 4. I keep the variable, I decrease the exponent by 1, which makes it a 1. Plus, I take the 1 from here, I multiply it by the 6, which gives me a 6. And then I keep my variable and I decrease the exponent by 1. That's 6x to the 0. X to the 0, anything to the 0 is equal to 1, you say. That really says 6 times 1, which is just 6. You're absolutely right. So our first derivative is equal to 4x plus 6. We want to find all of the points on the graph. Let's start out with figuring out when on the original graph there would be a tangent line with a slope of 22. We can do that by taking this fabulous function which generates slopes of tangent lines, and we want the slope of the tangent line to be 22. Let's solve this equation for x. Subtract 6 from both sides. Divide both sides by 4. There will be a tangent line to the original function at the point where x equals 4. X equals 4 isn't really a point on that curve, on that graph. Let's find the corresponding y value. So we like this, but now let's find the corresponding y value by plugging that x value of 4 back into our original function, not f prime. I'm plugging it into f now. So that is 2 times 4 squared plus 6 times 4, which equals 4, 16, 32 plus 24 equals 56. So the answer is x comma y. It's an ordered pair. 4 comma 56. So that is the point. It's the location of the point on the original function where the tangent line will have a slope of positive 22. Find all x values, if any, where this tangent line to this graph is horizontal. What's the slope of a horizontal line? 0. So we need to take the first derivative of the given function, set it equal to 0, and solve. You might want to write that down. It's going to happen a lot. Take the first derivative, set it equal to 0, and solve. I'm going to do those 3 things. If my paper will hold still. Y prime equals exponent of 3 multiplied out front is a 3. Keep the variable. Decrease the exponent by 1. Next term, Take the exponent, multiply it by the coefficient. That's 2 times negative 3 makes negative 6. Keep the variable, decrease the exponent by 1. Take the derivative of the third term. The third term's a constant. Derivative of a constant is? Correct, 0. Nice. Then, so this is, right, I said find the first derivative. That was step 1. Set it equal to 0. I said that was the second thing I was going to do. So there it is, setting it equal to 0. And then the third thing I said I was going to do was solve. In order to solve, I'm going to factor a 3x out of this equation so that I've got 0 is equal to 3x times x minus 2. Looks good. And then we'll solve that by taking the 3x and setting it equal to 0 and the x minus 2 and setting it equal to 0, which gives us an x value of 0 and an x value of positive 2. So those are the x values of a couple of points on the original function where the slope of the tangent line would be 0. In other words, where the tangent line is horizontal. I recommend that you take this original equation, plug it into a grapher, graphing calculator, desmos.com, desmos.com, see what this function looks like, find the points on the curve where x equals 0 and where x equals 2, and check it out. It's either going to be right at the top of a curve or it's going to be right at the bottom, like of a valley. This is a cubic. It's a third-degree polynomial with a positive leading coefficient, which means it's going to look something like this. And I would be willing to bet, is that necessarily true? Yeah, I'd be willing to bet that 1. I don't know where the x-axis is going to be, something like this, but I would bet that this is going to be the point at the top of a hill that has an x-coordinate of 0, and that there's going to be a point at the bottom of a valley that has an x-coordinate of 2. I was able to draw this because of the end behavior of my original polynomial that had an odd degree. It's a degree 3 polynomial, so it's an odd degree polynomial with a positive leading coefficient. I'm bringing all your college algebra and throwing it right back at you. All right, so that's how I was able to have a rough idea of what that function was going to look like. So now these more applied kind of concepts, we're in an elementary calculus class, which is predominantly for students in the College of Business. I think all of my elementary calc students are in the College of Business. And remember that economists use the word marginal to refer to rates of change, in other words, first derivatives. The next bullet, it says in green that a marginal cost or revenue or profit function is found by taking the derivative of the cost or revenue or profit function. And something that I don't work with all that often, being more on the pure math side of things predominantly, is this third bullet that says, remember that roughly speaking, the marginal cost at some level of production X is the cost to produce the X plus first item. And that actually makes a lot of sense if we think of it in terms of slope, because in order to get to that X plus first item, you would have to rise or fall some amount and then run 1. And the running of 1 in the calculation of slope is moving from your X term to your X plus first term. That plus 1 is the run of 1 in the X direction. So that actually makes sense, which is nice when that happens. Nice when it makes sense a little bit. If the marginal cost of producing an extra unit, so if the cost to produce that X plus first unit exceeds the marginal revenue, the amount of money coming in from selling it, then you would lose money on the production and sale of that unit. And we don't want that to happen, of course. So let's look at these next. I think we've got 2 more examples left. The total cost to produce X handcrafted wagons is this. Find the marginal cost, right? I'm stopping there. In order to find the marginal cost, I need to take the derivative. And then, once I have C prime, which is the marginal cost function, then we'll plug in our X value of 8. I'm going to just tell you what your marginal cost function is, and then if you would like to try to have figured it out on your own, maybe pause the video here, figure out C prime on your own, then push play, and I will write it down for you. So that's your marginal cost function. Unusual to have the variables or the variable written so the exponents are increasing as we go from left to right. Usually I feel like I would see this function written with the x cubed term first, and then the x squared term, the x term, the constant term, but it's okay, they're equivalent. And then the next thing we want to do in order to figure out the marginal cost when x equals 8 is to evaluate C prime of 8. I'm going to let you do the arithmetic on that one. I think you can handle it. And finally, demand functions. So I've already put some highlighting and a couple of arrows on here. A demand function defined by P equals D of Q relates the number of units Q of an item that a consumer is willing to purchase to the price P. You can imagine that often as price increases, the demand for that item will decrease because it gets too expensive for more and more people as the price goes up, so the demand goes down. That's probably not always the case, but I would bet usually that's the case. Okay, so again, Q is the number of items, and I've highlighted that in blue and drawn an arrow down here to this next equation in our actual example where we see the variable Q, and it's relating the number of units to the price P, and I've drawn an arrow down to P in this equation also. Revenue is related to both of those things, the number of items that you're producing and the price, or the price per item to the consumer. So revenue is equal to number of items times price per item. Now the number of items is the number of items, but the price per item is being determined by our demand function. The demand function returns a price that the consumer is willing to pay. Okay, so let's take that into the actual example. It says that we're to assume that the demand equation is given by Q equals. So Q, remember, is number of items. P represents price. Find the marginal revenue. Marginal, like, my mind stops. I read marginal revenue and I think, well, I'm going to need to take the derivative of the revenue equation. Marginal revenue. For a production level of Q equals 1,000. Okay, once I have the marginal revenue equation, which is R prime, I will need to plug in a Q value of 1,000. And then they want us to interpret what those resulting numbers mean. So let's do that. Let's figure out our revenue equation first. Remember that revenue is equal to Q times P, and our price is determined by the demand function. this demand function is interesting because let me get my highlighter here. Notice that this demand function, it does describe a relationship between Q, the number of items, and P, the price per item. Farther up the page, here we have a demand function that relates P and Q. The interesting thing is that the expression, the equation that I circled almost at the top of the page here, has P all alone on one side of the equation. In this equation, Q is all alone on one side of the equation. So now I'm looking at this thing and asking myself, so what do I need to modify this equation that I've been given so that Q, or rather so that P is all alone on one side of the equation? Well, revenue is definitely dictated by the number of items that I sell or the consumers are buying. So I think we have to leave R, the revenue equation, in terms of Q, which means I want to replace this P value with something in terms of Q. Well, what does P equal? I don't know. But we're going to find out because we're going to take this equation and we're going to solve it for P. So let's see, how should we... Let's write this as Q times question mark for the moment, okay? And then we're going to go up here and we're going to say Q equals 5,000 minus 100p, and then I'm going to, let's see, how should we do it? Let's add 100p to both sides so that this says Q plus 100p equals 5,000, and then I'm going to subtract Q from both sides so that 100p equals 5,000 minus Q, and then we'll divide both sides by 100 so that P equals 50 minus, right, because 5,000 divided by 100 equals 50, minus, and then you could write this as 1 over 100 times Q, or you could write it as Q over 100. I'm going to write it as 1/100th Q. That way it's like that 1 over 100 is a coefficient. I like that. So this is our question mark. So I think I'll go back to where I wrote this question mark in here, and I think I'll get rid of it. In fact, I guess I'll just get rid of all of that. And it's this P value that's now going to come back into here. So by substitution, we could, instead of using arrows, let's put a star here. And then we'll come back to the left and say by star, comma, this equals Q times 50 minus 1/100th Q. And then if we distribute our multiplication, this equals 50Q minus 1 over 100 times Q squared. this might be a problem that you're going to have to watch again. And I would say that one of the trickiest parts about this was that it's almost like they tried to trip us up by giving us a demand equation that was solved for Q instead of solved for P. All right. However, I think it's reasonable to have P as the independent variable and have the equation solved for Q. But in this case, in this particular example problem, we really needed it to be the other way around. We needed it to be solved for P. So we went through those motions over here, and then we plugged it into our revenue equation, which we had. And now we can find the marginal revenue equation. Marginal revenue equation is R prime of Q, which equals, take the exponent times the leading coefficient, that's a 1 times a 50, which is 50. Decrease the exponent by 1, so that makes Q to the 0. We don't have to write that. You can if you need to. Minus 2 over 100 times Q to the first power. You can write that if you need to. I'm going to write it as immediately 1/50th times Q. So this is my revenue equation, and now I want to know what's the marginal revenue for a production level of Q units. Good thing that Q is the only variable we have in our marginal revenue equation. If we had processed this by taking this equation as it was and plugging it in here for Q, then our revenue equation would have been in terms of P. But then they didn't give us a P value, they gave us a Q value. So how, we would have had to make some other modification in order to be able to plug in a P value instead of a Q value. So I think we made the right choice in this little modification that we did, solving that equation, the demand equation for P. So now let's plug in our 1000 as a Q value. We don't even have to write that. Let's just write R prime of 1000 equals 50 minus 1/50th times 1000, which is 50 minus, you could cancel a 0 if you wanted to, and then you've got 100 divided by 5, which is 20, which is equal to 30. And is that the answer to part of our question? Find the marginal revenue for a production level of Q equals 1000. I would say that the marginal revenue is 30 watts. I would bet that it's $30. And it's revenue, marginal revenue. Revenue is money coming into the register, so to speak, and it's $30 coming in. When is it that I'm making those $30? What's marginal revenue? It's the revenue that comes in on the Q plus first item. So in this case, selling the 1001st item would bring us in a revenue of $30. That's what our answer means. So that's great. It's nice to know that we would have $30 coming in from selling the 1001st item. Of course, the next thing we would want to do is to compare that to the cost of producing the 1001st item, and then we can compare the revenue and the cost and decide should we continue increasing our manufacturing and attempted sale of these items. If the revenue is higher than the cost, we keep going because that keeps profit positive. All right, so that was kind of a lot. I think it's great that you got to see some examples of taking the derivative by using these new processes, and then to roll that into a couple of applied problems was good. This last one, a little bit tricky, okay? But you don't want the practice problems that we're doing in these videos to be too much easier than your homework problems. I want to stress you out just a little bit before I send you off on your own. And the review that we saw of sort of the college algebra material of working with exponents and radical expressions and making sure that we can convert back and forth between those. If you need to brush up on that stuff, make sure that you do that on your own, with other videos, with a tutor, or in class, or in office hours. If you're not up on that stuff, your abilities and capabilities will only be as strong as your weakest link. Don't have that be your weakest link. All right, y'all. Thank you so much. I will see you next time.